Greetings, we are Lunar Oasis and this is our final project presentation for MEEM 4810 Introduction to Aerospace Engineering. Our team consists of Matthew Kenny, Dakota Sweeney, Owen Soulier, Travis Zuliger, and Jesse Justice. During this presentation, we will discuss each of the key aspects of research completed during the semester-long project. This includes our business model, costs, logistics, infrastructure, mining and refining operations, hazard analysis, and overall cost and feasibility reports. Taking a look at our business model, Lunar Oasis strives to revolutionize the deep space industry by providing lunar orbit refueling services, enabling cheaper and increasingly efficient exploration, research, and colonization. Our main customers are NASA, Boeing, and SpaceX, and we plan on making money by selling fuel at $10,000 per kilogram. In total, 97,000 kilograms of fuel will be sold to our customers each month, which is enough to fill a Falcon Heavy rocket's second stage. This means we will have a monthly income of $970 million US. Initial funding will come from companies and agencies as well as wealthy donors, all of which will support Lunar Oasis's goal of supporting humans in deep space exploration.
Lunar mining-based logistics. All of Lunar Oasis's critical infrastructure will need to be transported to the moon's surface via SpaceX's Falcon Heavy rockets. The Falcon Heavy rocket has a maximum payload of 63,800 kilograms to low Earth orbit. In order to reach the moon, each supply mission will need to refuel in orbit. For a full payload, the rocket will need to be loaded in orbit with 260,388 kilograms of fuel and oxidizer. Putting 260,388 kilograms of fuel in orbit will require 5 preceding launches. The fewest possible launches is 2, corresponding to a less than 16,169 kilogram payload. The initial supply mission is expected to be 70,760 kilograms and consists of 3,500 kilograms for the communications array, 21 1,000 kilogram rovers, 1 200 kilogram molten regolith electrolysis reactor, 1,300 kilograms of dried food, which is enough for 2 rotations, 1,760 kilograms of water for food preparation and hydration, also enough for 2 rotations, 45,000 kilograms of inflatable habitat. The initial supply mission will require 2 separate rockets. The first will carry the communications array, 11 rovers, the MRE reactor, 1,000 kilograms each of food and water, and the inflatable habitat's main module and airlock, for a total of 36,500 kilograms. The second will carry 10 rovers, 300 kilograms of food, 760 kilograms of water, and the 3 remaining inflatable habitat modules for a total of 36,060 kilograms. Each launch will require 3 preliminary fuel launches, for a total of 6 launches to be put in fuel orbit, or to put fuel in orbit. Non-critical lunar infrastructure will be constructed using lunar regolith and metals refined from a molten regolith electrolysis reactor. MRE byproducts are iron, aluminum, silicon, titanium, and glassy slag. Glassy slag can be used as a substrate for producing solar cells. Metal byproducts can be refined for using in additive manufacturing, casting, etc. The crew's oxygen needs will be met by collecting and storing gaseous oxygen at the MRE reactor's anode. Using a value of 1.26 kilograms of oxygen per person per day and a safety margin of 2.1, our annual production rate is estimated to be 2,000 kilograms per year for 2 crew members. The MRE reactor needed to produce 2,000 kilograms of oxygen per year will weigh approximately 200 kilograms and will require 8 kilowatts of electrical power.
The design of the mining-based infrastructure was one of the more important parts that we had to look at during our design process. We first had to determine a location that we were going to mine at, and then we started looking at structures that are going to need to be built while we're there, such as living quarters for our crew, method of generating power, storage for the resources we're mining, methods of communicating back to Earth, a launch and landing pad for all of the rockets coming in and leaving, and then the layout of the complex overall. And then lastly, we had to determine how this was all going to be built while we're there. The location of the lunar mining base is one of the first things that the Lunar Oasis team had to consider. 3 locations were considered. Peary Crater, which is located near the north pole of the moon, a cluster of craters near the equator of the far side of the Moon, and then a cluster of craters near the South Pole. Period crater is known to have roughly 1.3 trillion pounds of ice, but this is spread out over a very large distance and multiple craters within that crater. The far side of the Moon is known to have just as much ice, also spread out, but has only 2 weeks of sunlight followed by 2 weeks of darkness. This would be difficult for power generation. Also, being on the far side of the Moon would make communications difficult, as a second satellite would be needed to relay around the Moon. Ultimately, the team decided to go with the craters near the South Pole. These have a large amount of ice, roughly 1 trillion pounds, and have nearly constant sunlight, making power generation much easier. It also has an easy access point for communications and from a logistics standpoint. The team next had to look at the lunar habitat. The design selection process mostly consisted of what kind of building material or what kind of prefab building we were going to use. Top choices included inflatables, erectables, and lava tubes. Ultimately, the team decided to go with inflatable modules, as these are light, compact, and easy to assemble. They also are strong enough due to the internal pressure to have multiple layers of regolith stacked on top of them. The design of these modules was next up. The size ended up being an overall 360 cubic meters, including 4 modules, an airlock, and the connecting tubes. These inflatables will be covered with 2.5 meters of regolith to prevent radiation and micrometeorites from damaging the external shell. Life support will also be included in these modules to allow the crew members to live in them comfortably. Life support will include things such as air control, waste management, fire detection and suppression, crew care, and many other things. Lunar dust is one of the biggest issues the team will have to face during their time on the Moon. To help mitigate this issue, a landing and launching pad will have to be constructed. This pad will help limit the amount of dust that goes flying during the landing and launching processes. The design consists of 3 rings: a large, compacted, and sintered regolith center ring, a second ring that has large to medium rocks layered over compacted regolith, and a third ring that has small to medium rocks layered over compacted regolith. The outermost ring will be 170 meters across, while the internal ring of compacted and sintered regolith will be about 90 meters across. To produce the power needed for the lunar mining base, a large solar panel array will have to be constructed. About 120 kilowatts a day is what will be required of the base, but this will be scaled up to 200 kilowatts to account for worst case scenarios. Gallium arsenide-based solar cells will be used, which means about 8,000 square meters of solar panels will be needed. These will be located approximately 1,000 meters away from all mining activities and landing and launching pads to prevent as much dust as possible from gathering on them. There will also be a weekly cleaning event performed by the crew members present on the Moon to keep these clean and highly efficient. A line of communication will have to be maintained between ground support on Earth and the lunar mining base. To do so, 2 dishes will be constructed and placed on top of the lunar habitat module. These dishes will relay up to the orbital refueling station, which will relay to ground support on Earth. This will help prevent having to buy an extra satellite and put that in orbit around the Moon. 3 types of storages will be required on the lunar mining base: 1 for mined resources, 1 for fuel near the landing and launching pads, and 1 for all the equipment. The mined resources will have 2 separate tanks, 1 for oxygen, 1 for hydrogen, and these will be located underground. There will also be an underground fuel tank near the landing and launching pads so that rockets may be refueled when they land. Both of these will be climate controlled. Then there's the equipment storage. This will consist of compacted regolith and will not be climate controlled. To protect our crew and our equipment from the highly abrasive lunar dust, a dust-free zone will be designated. This zone will include the habitat, communication array, solar panel array, and equipment storage. It will not include anything to do with the mining operation, the landing and launching pads, or transportation corridors. It will be located a minimum of 500 meters away from all mining operations. There are many parts of the infrastructure that will have to be constructed in the future, but these are not required and will not be focused on by the Lunar Oasis team at this time. These include but are not limited to utility trenches, roads, lighting, and many other things. After determining what we were going to build, we had to determine how we were going to build it. To assist the crew in all of this construction, 1 excavation rover will be needed. This rover will be capable of rock sorting and digging and will be similar to the design pictured in the top right. Mining rovers will handle the launch and landing pad sintering, while the excavation rover will handle most of the digging, rock sorting, and will bury the habitat in a minimum of 2.5 meters of regolith. All of this material will be shipped to the Moon and assembled there upon arrival by the human crew.
Refueling station logistics. The low Earth orbit to L1 delta V requirement is 3.8 kilometers per second. Because the rocket will not be landing a payload, all 3 first stage tanks and engines can be jettisoned, leaving only the mass of the payload in second stage, which is 67,800 kilograms. The mass of fuel required to reach L1 is 169,697 kilograms, which exceeds the second stage's capacity of 97,000 kilograms. So the payload must be split between 2 separate transfers. The first transfer will be devoted solely to the crew module, which has a mass of 27,040 kilograms. The mass of fuel required to take a 27,040 kilogram payload from low Earth orbit to L1 is 77,690 kilograms. The second transfer will carry the 8,000 kilogram pumping module, the 5 3,000 kilogram tank modules, and the 1,800 kilogram robotic arm. The mass of fuel required to carry this 24,800 kilogram payload from low Earth orbit to L1 is 72,884 kilograms. A total of 149,774 kilograms of fuel must be placed into low Earth orbit in order to make placement of the refueling station possible. This amounts to 3 full fuel payloads, which must precede the launch of the refueling station.
Refueling station overview. The refueling station will have the ability to refuel 1 Falcon Heavy second stage rocket per month with the ability to scale production. Located at the L1 Lagrangian point between the Earth and the Moon, it allows the station to stay in the same spot with minimal thrust corrections. It's located close to the Moon compared to the other points, which requires less fuel and time. It's also easily accessible from the Earth compared to the other points. The components have a total mass of 51,840 kilograms. This includes the fuel tanks, pumping modules, solar array, crew module, and the maintenance module. The total cost of this will be $2.5 billion US. This figure shows a similar design to the potential Lunar Oasis refueling station. Modules. The tank modules will have a capacity of 20,000 liters each and a mass of 3,000 kilograms each. The modularity of these tanks allows Lunar Oasis to easily add capacity to the refueling station. 5 of these tanks will be used initially, 4 of them being oxygen tanks and 1 hydrogen tank. The pumping module consists of a computer system to autonomously control the pumps, valves, and piping of the station. The ability to pump in zero gravity will be possible due to inflatable bladders that will push the fuel down towards the fuel pumps. The mass of this system will be 8,000 kilograms. Refueling station modules continued. The crew/maintenance module will have capacity for 4 astronauts for 6 months. It will consist of an environmental control life support system, a power generation system that will have double-sided solar arrays and 90 kilowatt-hour batteries, a communication system that will support S-bands and Ku bands. A total mass of 27,040 kilograms is predicted. Refueling station robotic arm. The robotic arm is needed for berthing large rockets for refueling. Lunar Oasis design is very similar to the Canadarm2 on the ISS. It will have the ability to handle loads of 256,000 pounds, which is well under the predicted weight of the Falcon Heavy at 100,000 kilograms. This gives a factor of safety of 2.56, and the total mass of the robotic arm is 1,800 kilograms.
Mining operations relates to the method of extraction of water from the lunar surface. For this, 2 options were considered. The first being to use a microwave to vaporize ice and a cold trap to capture the resulting vapor. The second, strip mining to remove regolith and melting in a contained unit. In order to choose between the 2, a trade study analysis was utilized. Results for each category can be found in the following table, but at the end, the microwave system was chosen for its significantly greater durability. Mining operations are completed by a fleet of rovers similar in size to the Mars Curiosity. Each rover is equipped with battery electric power as well as a robotic arm to house the microwave and cold trap equipment. Additionally, climate-controlled tanks are included for the transportation of water, while controls and communication systems are also on board. Each rover is dispatched from the docks at the refinery in order to complete its mining procedures. Afterwards, it returns to the dock to deposit its water and begin the recharge process. An optimization of rovers was completed based on tank size, battery size, and overall quantity. Multiple factors were taken into consideration, and at the end it was determined that 19.24 rovers were required to meet the needs of the customer. Rounding up, Lunar Oasis will equip 20 rovers with mining capabilities in order to meet the needs. The table at the bottom shows the analysis that was completed and what factors were taken into consideration, including travel, mining, and docking times, as well as mining rates and ranges. This is only one of 3 tables that was used to complete the analysis. A rough model of rovers was developed in order to determine the rate of power consumption. Rovers were found to consume power at an average rate of 21.9 kilowatts. Overall, that means rovers can operate 4.57 hours at a time before requiring a 1.52 hour recharge. The table at the bottom breaks down power consumption by component, power usage, and percentage of operation. Refining operations relates to the method of refining water into rocket propellant. For this, multiple options were considered, including low and high temperature electrolysis, photocatalytic water splitting, nuclear thermal water splitting, and solar thermal water splitting. The table at the bottom displays the analysis that was completed in order to determine Lunar Oasis's best option. Total scores are accumulated on the right side, and it can be seen that low temperature electrolysis was found to be the best option. Breaking down the alternative options for refinement, low temperature electrolysis relies strictly on electrical current to separate elements, while high temperature electrolysis relates on heat as well as the electrical current to separate elements. Photocatalytic water splitting uses solar energy and a catalyst, while nuclear thermal water splitting uses heat from the nuclear reactor and often operates between 1100 and 1300 degrees Kelvin. Finally, solar thermal water splitting uses concentrated solar energy and operates between 1000 and 1500 degrees Kelvin. Electrolysis is a fairly simple process that can be explained at an elementary level. Essentially, it includes a tank with an electrical current passing through the water. Additionally, a plastic membrane is used to serve as an electrolyte to the process. When the current is passed through the water, hydrogen atoms collect at the cathode, while oxygen atoms collect at the anode. At this point, the gases escape from the tank into separate tubing systems where they are condensed and sent to the next process. Taking a look at the overall refinement procedure, it begins with the importing of water from the storage tank. Next, electrolysis is used to separate the hydrogen and oxygen atoms, where we end up with 88.81% oxygen mass and 11.19% hydrogen mass. At this point, the gases escape into their separate tubes and they are condensed before being loaded onto climate-controlled modular tanks for storage and transportation to the refueling station.
There are a number of barriers that must be overcome in order to maintain a permanent lunar base. Lack of gravity, lunar dust, and no atmosphere result in many difficulties in establishing infrastructure on the moon. These hazards are not present on Earth, besides dust to a lesser extent. Without proper mitigation, human functionality and health, as well as construction and integrity of buildings, would experience major difficulties. A lack of gravity can pose risk to astronauts, immediate and long-term, since our senses and physiology are tuned to 1G. Hazards that arise from a lack of orientation include falling over and harming the astronaut, flipping a switch the wrong way in an emergency, and misjudging the physics of a dropped or thrown object. The base must not have elevated surfaces without proper restraints to prevent falls in the event of disorientation or misjudged movement. As for disorientation leading to flipping a switch the wrong way, all instrumentation must be designed accordingly. Labels must clearly define which way is on and off to prevent mistakes in the event of an emergency. In a low-gravity environment, the convection process would be slowed down greatly, resulting in more stagnant air. Without it, our core body temperature can raise by 1 degree C. This increases the energy consumed by the astronaut. To conserve energy, the base must have artificial circulation of air to maintain natural core body temperature. Low gravity conditions cause muscle wasting and bone density loss when astronauts spend extended periods of time in space. The negative health effects of low gravity can be lessened by regular weight-bearing exercise to maintain muscle mass and bone density. Equipment required for this include low gravity exercise apparatus that revolves around whole body exercises. Moon dust is the result of millions of years of micrometeorite impacts that have pulverized the surface of the moon. The tendency of lunar dust to cling to things can make it difficult to see and take clear pictures. Having clear visors and camera lenses is important for mobility and safety, as well as recording data. Breathing lunar dust into lungs can cause serious health effects. Due to the amounts of iron in lunar dust, astronauts can experience iron toxicity. Dust can also cause inflammation, eventually leading to cancer. Dust poses hazards to the electrical and mechanical systems of the base. It can negatively impact electrical instruments by overheating, poor contact in relays, arcing and carbon tracking in higher voltage appliances, and creating difficulties to repair and restore instrumentation. Dust travels deep into mechanisms due to its small size. The abrasiveness of the dust can cause premature failure in parts. A double decontamination method will be used, as well as suits being kept in a separate room in the base with a negative air pressure to keep dust out of the rest of the base. There are an array of health hazards associated with not having an atmosphere. The longer a human spends in space, the greater the risk of developing cancer, aging, and decreased immune functionality from the radiation. Along with selecting individuals who are naturally resistant to radiation, there are ways we will further reduce risk of overexposure to radiation. Astronauts will undergo gene therapy to overexpress endogenous and exogenous antioxidants and repair genes. Placement of the base is crucial since temperatures as low as -238°C have been recorded on the moon. The base and rover mining equipment storage area will be underneath several feet of regolith to insulate them from extreme temperatures. When a large meteorite impacts the moon, large clouds of dust and rocks are shot up and rain down tens of kilometers away. Micrometeorites also pose a risk. Meteor showers will need to be monitored in order to protect astronauts and equipment from potential impacts, since fortifying equipment against these impacts would result in great loss of mobility. When taking off from Earth, a spacecraft must be protected against the great heat and forces experienced when exiting the atmosphere. Without these, and the lower gravity of the moon, launching and landing on the moon is much safer. However, there is a hazard of dust being blasted up and away from the takeoff and landing site. The forces experienced on the lunar dust would send particles flying at high speeds. Due to the abrasive nature of the dust, anything nearby would be significantly damaged. The takeoff and landing pad would need to be a considerable distance away from any outside astronauts and exposed equipment or infrastructure.
Cost analysis. This is the 4-year budget plan for Lunar Oasis. As you can see, the manufacturing cost during the first year is $8.155 billion. The initial shipping cost is $1.322 billion. The cost to assemble everything is $9.758 million. Yearly costs total $4.7 billion based on the 2018 projected budget for the ISS. Rocket fuel sales total $11.64 billion per year. And at the end of year 1, Lunar Oasis will be $2.5 billion in debt. However, costs are quickly recouped as time proceeds.
After drawing up a plan and performing a detailed cost analysis, the Lunar Oasis team has decided that this project is not currently feasible. The space travel industry has not reached a point where customers will require our service enough to balance the cost of recurring expenses. Lunar Oasis will archive this report and reevaluate the feasibility for the project if the financial climate changes.
References.